So, lecture 4.7, random variables. Probabilities, which we've been talking about, are useful even when they do not deal strictly with events. It often occurs that we measure something that has randomness associated with it. We use random variables to represent these measurements. So, so I'll just jump in. A random variable, x, is a function that maps something from the sample space, omega, which is the space of all possible outcomes of an experiment, right? So something from that. So it takes that and it assigns a real number to it. And we take a specific outcome from the sample space to be omega, small omega, and sample space to be big omega. Real number we say is x, and the map is capital X. A random variable will be denoted with a capital letter, typically, although not all the time, because we kind of are not good at consistency. And a specific value that it maps to, the image, will be denoted with a lowercase letter, for example, x and k. So let's take a look at this figure. So we've got our sample space. So these are all the possible things that can happen in the experiment. We take an outcome and we map it onto a real number, and that real number that map to the real numbers is called a random variable. So, for instance, if you were to take a thermometer, all the possible temperatures that you could be at, you could use that as a random variable, and you could assign it some real number to represent the temperature. That one, I think that oftentimes we skip this conceptually and we just say, oh, it's just a continuously varying variable, and so it's a random variable. The fact that it has randomness associated with it is what differentiates it from just any old variable. So, great. So it's really, it's conceptually there's not a lot going on here, but we get to start to see cool stuff now. So there are two different types. A discrete random variable, k, is one that takes on discrete values. So for instance, we might say that a temperature can only be the real temperature varies continuously as a real number, right? Like you can be anywhere in between any two temperatures that you choose. So if you say you're at one temperature and another object's at another temperature, there are an infinite number of temperatures in between those two temperatures, right? That's a continuous thing, a real number that describes a continuum. It's also what? Time dependent. Also time dependent, right. So at a given time, we often would say. A discrete random variable might be one, so discrete events like rolling of die, or like something that's detecting defective parts might be like, one outcome might be defective and the other outcome might be not defective. That would be a discrete random variable as well. So it has only two values. But you could have one with more values too. You could have one that's like horribly deformed. Anyways, dice again as an example, because we like dice.
Six-sided.
Dice, just the regular old six-sided Monopoly dice, backgammon dice. We're gonna start talking about them soon, but this is our last hurrah with dice. We don't want to move on without a little bit more dice rolling.
Six-sided dice, or are you referring like this is the last hurrah with any and all dice?
We should come up with a catchphrase in the class, like, no dice.
Or let's roll.
Let's roll. There's a good one. Let's roll.
Nice.
No dice.
Our catchphrase is help.
It's a good catchphrase.
Oh, see, that's very accurate.
Living on a prayer. Okay, yeah. Roll two unbiased dice. Let k be a random variable representing the sum of the two outcomes. So the sum of the two dice, whatever they faces up, and laces out. So let P of K be the probability of the result K. Plot and interpret the probability of K. All right, so let's draw ourselves an axis. And this will be K. And it's going to start out here, and this will be 0. And we're going to plot the probability, which I'm... okay. So what is the probability that you sum up... Watch this, you guys. Want to see something fun? Okay, and then now watch. No hands besides the one that's on the keyboard. Evenly spaced. Love it. Okay. All right. So we have ourselves a nice axis here with some number of ticks. Hopefully the right number, because I didn't count.
You should title this video Hacking Illustrator.
Ooh, yeah. Actually... No. Okay.
Maybe with a question mark.
I think I am gonna need more.
You need 10, right?
I need 12.
Why do you need 12? Okay.
They're not. Oh, they're so bad. So bad. That is called the propagation of error right there. A cumulative error. All right. So we have way too much drawing of these things, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what is the probability that the sum is 1?
Not 0.
0. So I'll draw a little like circle at 0. So the probability of the sum being 1 is 0. Probability of the sum being 2.
1 out of 36.
1 out of 36, right?
Oh, yeah.
So it's 1/6 times 1/6. 1/36. And then what about it being 4? Or no, 3. 3 is next.
1/18.
1/18 is correct. What about 4?
Double that thing.
It's 1 out of 12. And we continue going up. One more. And we have 1 out of 9. And then we have the sum being 6. We have 5/36. I know. The obvious one. 5/36.
That makes sense.
And then we go up to our peak, which is what? It's probability of getting a 7 as the sum. 1/6. And then descend
The same way.
the same way that we went up.
Except for this one.
Except that an
You guys are harsh, man. My therapist agrees.
Ashley agrees.
No. Just my therapist. So, yeah. This is what the plot looks like. And it turns out that this is a special kind of thing. This is called a probability. Didn't leave myself room. Mass function. Probability mass function. And it tells you the probability of each of these outcomes. So what if you summed up all of these? What would you get? You better get 1. Yeah. Okay. Good. So there is your dice again. now we're going to talk about something besides dice. Special request from Jordan. You're welcome. Johnson-Nyquist noise. Yeah, I know. You've been waiting all this time. A resistor at non-zero temperature without any applied voltage exhibits an interesting phenomenon. Its voltage randomly fluctuates. You can measure it. It just like hook it up to, just a resistor and connect it to a really sensitive voltmeter, and you can measure yourself some Johnson-Nyquist noise. So it's called the Johnson-Nyquist noise, and it's the result of thermal excitation of charge carriers, electrons typically. And so anything that's at a non-zero temperature is going to have this happen. For a given resistor and measurement system, let the probability density function FV of the voltage across an unrealistically hot resistor be this. So probability density function is something that we haven't talked about yet, but we're going to talk about next time in great detail. But we're introducing it now because V is a random variable here, because it's something that's randomly varying continuously. It's a continuous random variable. And this is going to describe a very specific, what we're going to call Gaussian distribution of the noise. Okay, you guys probably heard that term before. It's a very, very commonly used model for a lot of different things, statistical things, especially noise. So we're going to plot and interpret the meaning of this function. So if we plot it, I kind of want to use black as the axis. Jeez. It's not my intention. But it's what happened, so we're flipping. All right, so what happens if you plot this function is that it tails off, and then it comes up, it peaks at the origin, and then it symmetrically tails off over here. It's supposed to be symmetric. And this is the voltage, of course, and this is FV. And what we have is, this is approximately 1, 2, 3, actually that was a little exaggerated, but 3 should be out here more. But in any case, this is approximately the behavior it exhibits. So we know that this is an unrealistically large amount of noise because we know that a voltage fluctuating up to 3 volts randomly with no excitation would be like crazy, right? But I did it because we didn't have to worry about talking about standard deviation and those types of things that we haven't introduced yet. So I just use this because it's round numbers and easy. But how we interpret this is that the probability, so with a continuous variable, we run into this sort of continuum problem where if you were to assign a probability to every point like we did in the previous example, we have an infinite number of points, so you're going to obviously have to sum to greater than 1 because unless you have infinitely small amplitude on all of them, which is, once again, not working for it. So we are stuck with this need to have a sort of continuum interpretation. And so how we do it is we say the probability that a voltage across the resistor is between, say, 1 and 2 volts is the integral of this function. That's why we call it a probability density function. It's the probability per unit volt, you could say. So you integrate over some interval, and then you get out your probability that it's in that interval.
Can we just look
There's also a chart. We'll talk about charts. We'll talk about chart. So there's two distributions where we use this a lot. There's also the student's T distribution, but that's the interpretation that we'll often. Well, the tables are just really nice because you don't have to do any integrals. But yeah, you guys, integrals aren't hard. We have tools for that. We have Mathematica and MATLAB, and you guys are just giving me pins and needles stares. Daggers.
These are tables.
All right. So that's all I've got for you for random variables. Any questions on random variables? We're going to expand on these probability density functions and probability mass functions next time. But
How likely is that?
I don't know. I feel like there's something growing at a very fast rate right behind my forehead. So I don't know if that means that I just have a headache this afternoon. But given everybody getting sick,
The fastest cancer ever known.
yeah.
It was 1 out of 2 chances.